In section 1.7, we want to start talking about functions, and we're going to look at how we can represent function as rules and as tables. Okay, so now when you think of a function's rule, it's like the equation that represents the function. And our key vocabulary for this section are function, domain, range, independent variable, and dependent variable. Now when you think of a function, function generally relates two or more different items to each other. So the example they're giving here is when you're pumping gas, the cost depends on the number of gallons pumped. So there is a relation between the number of gallons and the cost. And the cost would be said to be a function of the number of gallons pumped. So in this particular case, the function would have a domain, which are all the inputs. In the case of this particular example, the inputs are the number of gallons pumped. It's also called the independent variable. It's because I can pump however many gallons of gasoline I want. So it's relatively independent in terms of how many gallons are going to get used. So a set called the domain that contains all of the inputs, so that would be all of the possible different numbers of gallons I might pump. If I had a 20-gallon gas tank, that domain would be between 0 and 20. I can't pump less than 0 gallons, and I can't pump more than 20, so that's what it would look like. And then the range would be the cost from 0 gallons to 20 gallons, and those would be the outputs. And then a pairing of inputs with outputs has to exist such that each input has only one output. Okay, now different inputs can have the same output, but one input can't have two different outputs. Right? So we'll talk about that more as we look forward. So a function may be represented by a rule, and the rule would look like an equation that relates one variable to another, x to y, right? Or in this case, gallons to cost. The input variable is the independent variable. We choose it independently, and the output variable is the dependent variable because its value depends on which input was put into the function. Right? So if we take a look here at this table, if we want to identify the domain and the range, the domain is the collection of all of the inputs. Well, the inputs are these. So 6, 12, 21, and 42. And when we talk about the range are all of the outputs. So that would be 5, 7, 10, and 17. Okay, so the domain is a collection of all the inputs, and the range is the collection of all the outputs. Now, if you take a look here, a function may be represented by a mapping diagram, and that's where you map the inputs to the outputs. So now it's a different way. Here we related, right, when the input was 6, the output was 5. When the input was 12, the output was 7. So here we have them closely related. You might often see this as an input-output table or a T table or an XY table. Here they're mapping with arrows. And you'll notice that I have 4 inputs, but I have only 3 outputs because 2 of the inputs map to a single output. That's okay. It's okay if the output for 3 is 2 and the output for 4 is 2. That's not a problem. Where it would be a problem would be if 3 had 2 outputs. Then it would not be a function. Okay, so no input is paired with more than one output. We want to look at this and see, is this a function? Well, 1/2 is mapped to 0, 2/3 is mapped to 1, but 3/4 is mapped to 2 outputs. Okay, so that's a problem. A function is a relationship in which for every input there is one and only one output. So because of that, we would say this is not a function. So in a mapping diagram, you're looking for 2 arrows coming out of an input. If it was a T-table, you'd be looking to see, did a specific input show up more than one time with different outputs? that would also be an indication that it was not a function. So when we take a look here, we're looking at how making a table for a function. And tables can be made a lot of different ways. They can be horizontal like this. They can be vertical, however we want to do it. What we want to do is, in this particular case, we're going to make the table using these domain numbers. So remember, the domains are all the inputs. So here are my inputs: 0, 5, 7, and 10. And then my outputs will be the result of plugging these in. So when x is 0, 3 times 0 is 0, plus 4 is 4. When x is 5, 3 times 5 is 15, plus 4 is 19. When x is 7, 3 times 7 is 21, plus 4 is 25. And when x is 10, 3 times 10 is 30, plus 4 is 34. Okay, so that's making the function, and my range then, let me put the range underneath the domain, 4, 19, 25, and 34. Okay, so what we end with here in this key concept, you can see they've got a verbal rule here, which is a description of the relationship. The output is 3 more than the input. If I made that an equation, right, 3 more, that's plus 3. So we put y is equal to x plus 3. And then with a table, I select inputs, I plug them into the equation, and I get outputs. Okay, so we can either make the table based on the equation, we can make the equation based on the table, we can make both based on the verbal rule. You just want to have the flexibility to be able to represent this relationship in a number of different ways. Okay, so now my goal here is to write the function rule. So what I'm trying to figure out is what happens as I change from thing to thing. So what I'm going to kind of look at here is what is going on as we move from item to item. So when I move from 15 to 20, that's a change of 5. And when I move from 7 to 12, that's a change of 5. When I move from 20 to 21, that's a change of 1. 12 to 13, that's a change of 1. Okay, so it looks like there's just, as the change in x was 5, the change in y was 5. So it really looks like y is going to be equal to something like x plus some number, right? Because if every time x changes by a number, y changes by the same number, then there's no coefficient here. Each time this changes by 1, that changes by 1. So it's really about this. Now let's look at the difference here. 15 minus 7 is 8. 20 minus 12 is 8. 21 minus 13 is 8. So you can see y is always 8 less than x. So that would be adding negative 8 to either side. Or I could say y is equal to x minus 8. Okay, so what I did is I looked at how does y change as x changes, and I also looked at the difference between x and y, repetitively looking for patterns. Okay, and there's my functional rule. Okay, if I wanted to work in a real life situation, I'm buying concert tickets that cost $15 each. I can buy up to 6 tickets. Write the amount of in dollars that I spend as a function of the number of tickets I buy. Okay, so if it's the amount, right, the amount will equal the number of tickets times the price of the tickets, right? I don't have any kind of a ticket handling charge. If I did, that might have to be added on, but that's not in this problem. Identify the independent variable. Well, the independent variable is going to be the tickets. Okay, the independent variable is the tickets because the price is going to depend on the tickets. It also says I can only buy up to 6 tickets. So that means my domain and I can't buy a half a ticket. So my domain is going to be 0, 1, 2, 3, 4, 5, 6. I could not go to the concert and I could buy anywhere from 1 to 6 tickets, but I can't buy half a ticket, so it's not a continuous thing, right? These are very discrete. If we look at the range, then the range is going to depend because, again, the range is the output and it depends on the input. It's going to be 15 times the ticket price. So this would be 0, 15, 30, 45, 60, 75, and 90. Okay, so write the amount I spend as a function of the number of tickets. So the amount I spend would be equal to 15 times the ticket price. Okay, and that's going ahead and taking a real-world situation and creating a function rule in a relatively simple problem. That's it for 1.7.